Welcome to the session A21, Testing and Debugging. My name is Tingting Yu from University of Kentucky. I'm the session chair. Okay, so today we will be having 6 talks. And the first talk is opening the box on app developer security rationale. Will be presented by Dirk van der Linden.
Hi everybody, I'm Dirk van der Linden and I'm going to talk to you today about the paper Schrödinger Security, Opening the Box on App Developer Security Rationale. First, why did we do this study? We're a consortium of multiple universities spanning the University of Bristol, the Open University, Exeter University and industrial colleagues from Google, really interested in understanding what drives developers to do things securely or not. And specifically in the context of this study, we're very interested in mobile app developers as their demographic has expanded significantly and it's no longer the domain of a select number of developers with deep technical skills, training and knowledge that are working in well-established organizations with lots of support structures available to them. So you have lots of app developers who still need to do all the typical things across software development that go beyond just writing code. People need to set up their way of working. They need to actually write and test code, solve the problems that they run into. They need to deal with monetization to actually make a living from the things they do, and they need to deal with all the factors of release. And this increasingly diverse demographic of app developers has much less recourse to just say it's someone else's problem or someone else in the organization will take care of it. So we're really interested in understanding how this diverse crowd of app developers actually deals with all these kind of questions that might arise that go beyond just code, and to what extent they really consider security in those different tasks. So to that end, we ran 2 empirical studies where first we tried to really understand in depth what kind of behaviors app developers would exhibit and what kind of rationalization they would show over those kind of behaviors of different software development tasks, and whether that would actually correspond with a wider cross-section of mobile app developers. So we first ran a detailed empirical study with a number of app developers where we used a task-based approach, where we had a number of different tasks corresponding to the picture you saw earlier. For example, developers had to set up an integrated development environment where they were given a task where they could select only a maximum of 3 functionalities from the plugins that they could enable, where some of them would definitely contribute to security, such as static code analyzer with security checking rules, and others would be supportive of other factors. And we looked there if they actually selected things that do security or not. Similarly, we looked at how they actually deal with fixing source code. And in this case, as you can see in the full paper itself, we gave them an entire piece of code with different concerns in them and saw what they would fix first. We then also created a number of different tasks to focus on the other non-code related tasks, where we asked participants to sort what kind of choices they would do and what they would prioritize. For example, if we were asking them what they would do when they had no idea how to really deal with a particular API, they had to sort a number of options that included things like reading the official documentation or just asking another app developer you might know, or go to Stack Overflow and copy paste like we know people will do. And in these sort tasks, we basically checked whether the options that from literature we know prioritize security are sorted to the top, so prioritized, and the options that we know are quite bad for security are sorted to the bottom, or prioritized. Now, importantly, after that, we also asked every participant for their rationale for each task, how they solved it, why they think they did it, so that we could understand through a qualitative thematic analysis whether the decisions they made were actually grounded in a rationale of security or something else. Following this in-depth study, we conducted a larger survey using a simple Likert scale, where we had a couple of hundred Android app developers basically write whether they think the security of apps they develop are affected by decisions they make on the same topics that we had participants do tasks on in the first part, just to see whether the kind of attitude and whether the kind of secure solution and secure or insecure attitude would actually generalize to that wider angle. So what did we find? Well, interestingly, we saw that in the left hand of this graph, the distribution of solutions in the terms of the answers that participants gave was quite binary, that across a lot of the tasks you would have about half-half secure solutions and half non-secure solutions, that is, solutions that do not prioritize security. Although the two tasks that are heavily focused on social aspects, such as seeking help on a confusing API and seeking testers, showed far less solutions prioritizing security. What is particularly interesting is when you look at the quantification of the rationale analysis, that is, which solutions actually had a rationale indicating they made their decision on basis of security considerations. And as you can see, task 2, where participants were faced with source code, actually has a fair amount of participants considering the security, whereas the other tasks don't have that at all. So you have a lot of cases where tasks are solved securely, but not with a security rationale. Now, in a more in-depth qualitative analysis of understanding the rationales and seeing which ones would relate to security or something else, we performed a thematic analysis, finding a number of themes that coincided with developers giving a security rationale, such as trusting in other developers, understanding permissions are important, but also more simple dogmatic approaches like not assuming users are predictable, don't testing by yourself, which give more of an insight which you can read in the paper on really why developers reason the way they do. Now, when we compare that to a wider cross-section of Android app developers and their attitude towards these different tasks and whether they think that this affects the security of apps, we see a rather similar approach, that the code-facing tasks, so simply saying the code I write and the external SDKs I integrate into my code, those are seen as strongly affecting the security of your app, while a lot of the other tasks, such as the social tasks as involving testing, what sources you go to for help, or simply dealing with the license your software development is released under, those don't particularly seem to affect security in software developers' views. So what that means is that we basically see software developers, even though they may act securely across a variety of development tasks that aren't just dealing with code, their rationalization for security really only emerges when they're facing code or when they're actively thinking about code. So to that end, we recommend a number of things to ensure that these kind of software developers, which don't have all the recourse of organizational support structures and people to go to do things for them, that we need to make sure they also understand the potential security impact of all the different tasks and how important it is to reason about that security impact. So to that end, we have a number of takeaways. In particular, and most important, is to ensure a more critical attitude towards security among this increasingly diverse crowd of developers. And we need to really promote critical reflection on particularly social aspects. So what people do you trust and what resources do you trust that you need to rely on because you are such a small scale or even a solo developer which doesn't have all those other support structures. In the same vein, solo and small-scale app developers really need support to make the right choices in terms of security, not just for code. We understand that there is a lot of work on teaching software developers what you have to do right in writing secure code, what kind of vulnerabilities you have to avoid. But developers need a lot more support also in those tasks that don't have to deal with code. So research could, for example, focus on incorporating support for such activities within IDEs in a manner that's unobtrusive to the fluidity that software developers desire. And finally, to reason about security and to actually act upon it, in particularly among all those other tasks, we should really encourage software developers to take a user-centric view to understand the consequences that vulnerabilities have for their users, to basically shift the notion of software vulnerability as an abstract thing to understanding how the actions and the decisions they take in different software development tasks may have negative impacts on their users. So that's the overview of the two empirical studies we've done for this paper. I invite you all to take a look at the details in the paper itself. Check out our project website on www.writingsecuresoftware.org and ask us any questions, comments, suggestions you have. We'll be online here to chat with you. Thank you very much.
Okay, so thank you for the talk. I don't see there are any questions from the audience. Myself has a question. So you mentioned 4 tasks in your slides. That I wonder that why were tasks 1 and 2 are choice, but are not sorted?
Yeah, that's a good question. That's mostly because in those tasks, especially where people faced code, you wanted them to really interact more naturally with the thing. And practically speaking, it doesn't make sense to ask people to sort how they would approach a piece of code. So there, similarly, to measure the actual prioritization, we made it a much more urgent thing to say you only have time for one part to really get to the, really the key thing they would prioritize.
Okay, thank you. So we got one question from the audience. Excellent work. Did you analyze whether developers act upon a software development lifecycle like Microsoft SDL?
That's a really good question, and that's actually one of the key things that this work is really about, showing why we need so much more insight into a diverse crowd of developers, because you have these increasingly young solo, small scale developers, maybe working out of their basements, their garages, and they just start programming, they just start making things. And even if they might be aware of those kind of secure methodologies, they don't tend to really use it. They just tend to have, some insight into what's done, what people can really use, like OAuth top 10 and such, but they don't really tend to stick to key methodologies.
Okay, thank you, Dirk. Let's thank the speaker and move to the second talk. So the second talk is Smart Gray Box Fuzzing, presented by Sean Fair.
Hello everyone, I'm Ton Pham from the University of Melbourne. Today I'm going to present Smart Gray Box Fuzzing. I joint work with Marcel, Andrew, Alec, and Abik, who are currently working at Monash University, Veracode, UiPath, and the National University of Singapore. This is one of the first work to make gray box fuzzing input structure aware, and is dedicated for program taking highly structured input by a chunk-based file format, which is the common target for attackers. Our findings show that there are hundreds of CV discovered in this kind of program every year, and the number keep increasing. In today's talk, I will first identify the limitation of the current gray box fuzzing approach in handling chunk-based file format. Second, I will talk about our smart gray box fuzzing approach and the tool that we implemented. Lastly, I will talk about some experimental results showing the effectiveness and efficiency of our approach. First, let me talk about the normal gray-box fuzzing, how it works. This is the common workflow of the gray-box fuzzer like AFL. It takes some sample input and to select some input from the sample input, mutate this to basically slightly modify it and generate another set of input before sending the input to the system under test. And if the input trigger any new behavior like cover new branch in the control flow graph, the input will be retained for the next fuzzing round. However, this has a very critical limitation. It doesn't have any information about the input structure. So it views the input as a bit string. And because of that, it's only apply the simple low-level mutation operator like bit flipping or adding boundary values or doing some insertion and splicing of another bit string in a random way. Because of this limitation, it doesn't work well for input structure file format like PNG. This one I saw the presentation of the PNG file format, which is in a tree-based structure. In this one, we see multiple chunks, and each chunk could have another attributes, and we have the internal relationship between the attribute in the chunks. So the low-level input mutation operators like in AFL can quickly invalidate the relationship here. So turn the valid input into the invalid input, and it is very unlikely to produce the chunks, the whole valid chunk for the input file. To tackle this problem, we propose an approach to make the gray-box fuzzing input structure aware by doing four things. First, we change the representation of the input from the bit string to the tree-based representation. Second, we add new mutation operators to the fuzzer by making it working at the chunk level. Third, we prioritize the valid seed input over the invalid seed input. And finally, we also apply several optimizations to retain the fuzzing efficiency. First, let me talk about the new representation. We design a high-level structure representation called virtual file structure. The data structure consists of chunks and attributes which represent the data chunks and data fields. Each chunk can be parents of another chunks. Moreover, each chunk and attribute has the indexes maintaining the start index and the end index, allowing us to map it back to the physical input. Based on this data structure, we design a new component for gray-box fuzzing. We call it FileCracker. This component takes a seed input along with an input model, which is written in XML-based file format, and it will transform the input to the tree-based file structure. Moreover, this component also output the validity score of the input, and using this information, we can design algorithm, the selection algorithm to favor the one that is more valid. You may have concern about the manual effort needed to write the input model. However, in our paper, we presented a guideline which allows users to write input models faster and in a systematic way. Since we can represent the inputs in highly structured tree-based representation, we design a set of mutation operators which can work at the chunk level. Specifically, we can do the chunk deletion, chunk addition, and chunk splicing together with the low-level bit mutation operator. And we design and implemented our tool AFL Smart on top of AFL Smart on top of AFL by integrating the component that I have presented. We evaluated our approach in comparison with the state of the art in gray-box fuzzing, smart black-box fuzzing, and 10-based gray-box fuzzing in 15 real-world programs that take 10 different file formats as input. And the results show that AFL Smart clearly outperformed the selected baseline in both the branch coverage and the bug finding. Notably, AFL Smart doubled the number of bugs found in the selected benchmark compared to all the baseline, and AFL Smart discovered 42 zero-day bugs, in which 23 were assigned the CVE. And we released the source code, and it's get the attention from both industry and academia. And there are a lot of users who start our repository. Our work also has been featured on media and also has been integrated to the Google FastBind for independent evaluation. And the tool is available, so please try it out. And we have 17 input models which are available on the system, so we can easily use this. And please try it out. Thank you.
Okay, so thank you for the presentation. Let's see. I have a question. So for the input format model, do developers need to manually specify an input format?
Yes, the developer need to write this one, but there's some important point here. First, in the paper, we do explain how the developer can write this one in a systematic way. Second, one input model can be used for all the programs that take the same file format. For example, the people can write the input model for PNG file format, and it can be used to test all the programs that take the PNG as the input. So it's some effort that worth the benefit compared to another approach.
Okay, we got a question from the audience. Have you compared the approach with random input generation from the models?
We did basically we compare this one with the pitch phaser, which is one of the smart black box phasing, and we use the same model. So pitch phaser is a black box one, and our approach is a gray box one, and we compare and we clearly outperform this. Please take a look at our paper to see more detail about the comparison.
Okay. All right. Thank you. Thank you for the presentation. So let's move to the third talk, which is also a journal first paper, deep transfer bug localization.
Hello everyone, my name is Xuan Huo. I come from Nanjing University. Today we will introduce our work, Deep Transfer Bug Localization. When systems grow larger and larger, many projects often receive more bug reports than what they can handle. Bug localization is a technique that helps developers to automatically facilitate fast and efficient identification of the buggy code, which is very important and necessary. However, there contains several challenges in locating buggy source code in a new project. For example, sufficient bug data is often unavailable for new projects, which is hard for building a specific classifier based on supervised learning. Second, data distribution is different in a new project. Directly applying trained model is not appropriate. Therefore, cross-project bug localization is necessary. A question arises: how to deal with cross-project bug localization? In our work, we propose a novel cross-project bug localization model, which employs transferable feature extraction layers to learn common feature representation from source and target projects, and then learn different classifiers in the project-specific prediction layers. First, bug localization can be formalized as a learning task, which attempts to learn a prediction function to predict the related label of pairs of bug reports and source code. In the cross-project bug localization, the settings are similar. The data in the source project is available for training, but there is only a small number of data in the target project is available. Therefore, the key part for cross-project bug localization is how to transfer knowledge from source project and build a domain-specific domain model for target domain. Firstly, considering transferable knowledge, some common knowledge between the source and target projects should be captured such that knowledge learned from the source project can eventually be transferred to facilitate learning for the target project. Our solution is we design two convolutional neural networks that sharing weight to learn semantics of source code in both source and target projects. Second, considering domains specific, the source and target projects may differ in how their bug reports and source code files are correlated. We design two fully connected networks to learn mapping of source and target projects in the project-specific prediction layer. This is a general framework of our model, CHOMP-CN. The model contains four main parts: input layer, transferable feature extraction layer, project-specific prediction layer, and output layer. The training process and testing process are different. Bug reports and source code that from source and target projects are used for training, but only target project bug reports and source code are used for testing. In the transferable feature extraction layers, we apply two convolutional neural networks to extract semantics from bug reports and source code, respectively, and such knowledge learned from the source project can eventually be transferred to facilitate learning for the target project. In the project-specific prediction layer, two fully connected networks are designed to model the relationships between bug reports and source code in the source and target projects, respectively. And we propose a following hybrid loss function to fulfill the learning objectives for both source and target projects. The first term in the loss is the source project, and the last term is the loss in the target project. Here are some experiment settings. The dataset we used for evaluation is all open source software projects, and some widely used metrics such as top K rank, MAP, and MRR is used in our experiments. The first research question we want to study is there a need for a specialized technique for cross-project bug localization? In the table, NPCNA means within project bug localization setting, and NPCNP means only used a very small number of data in the target projects. NPCN is using within project bug localization model directly on cross-project setting. So the results that NPCNA is better than NPCN shows that directly using within project bug localization model for cross-project tasks is not good. NPCNP is worse than NPCN, means using cross-project data is able to improve the prediction results in the target project. So in summary, the results show that a specialized technique for cross-project bug localization is necessary. The second research question, we compare Chomsky with previous state-of-the-art methods, including within project and cross-project bug localization methods. In all 60 cases, Chomsky performs the best on 53 baselines, which demonstrates that the improvement achieved by Chomsky is significant. The third research question we want to investigate is that do the weight sharing strategy and the project-specific prediction layer in Chomsky improve bug localization performance? The results shows that Chomsky outperforms NPCN considering various standard metrics, so that our strategy work. In summary, our main contributions can be summarized as twofold. We propose a deep transfer learning approach specialized for bug localization named Chomsky, which extracts transferable semantic features from source project and fully exploits labeled data from target project. The comparison results demonstrate the effectiveness of our model. That's all, thank you. Thank you for your attention.
All right, thank you for the presentation. So since the presenter is not here, we are skipping the QA session. So now let's move to the next talk. The next presentation is also a journal first paper titled A Benchmark-Based Evaluation of Search-Based Crash Reproduction. And yes, go ahead.
Yeah, okay. Can you see my slides? Yeah. Okay. Hello, everyone. My name is Puriya Darakhshanfar, and I'm a PhD student in Delft University of Technology. And today I'm going to talk about the study that we published in Empirical Software Engineering Journal called A Benchmark-Based Evaluation of Search-Based Crash Reproduction. First, let's see what's the crash reproduction and why we need a search-based technique in general. When a user works with a piece of software, it's always possible that he or she makes the application crash. And when we have a crash, we have some information about the crash. For instance, the stack trace, which gives us some information about the type of the exception and active method calls during the crash happening. Those kind of informations are usually reported via an issue tracking system or an execution log to developers for debugging purposes. For instance, here we can see a report, an issue report in an issue tracking system of our industrial partner, XWiki. Here we have some information like the stack trace, but also we have an interesting piece of information. which is the scenario in which the crash happened. If you have those kind of scenario, and if you write a test according to that scenario, you have a crash reproducing test. And that test case or the test suite can be helpful in the debugging. And also after fixing the bug, that test case can be used in regression testing to make sure that the bug will not reappear in the next updates. But the point is that if you don't have that scenario, and if you're not a knowledgeable developer, it's hard to write that test case. It will be costly and labor intensive. So this is the reason that lots of approaches have been introduced to automate these tasks. Among these approaches, we have EvoCrash, which is a search-based software testing technique. And it takes the binary file of the application and a crash that happened in this application. And then it performs a genetic algorithm, a search process, to generate a test case that when we execute it, we have the given crash. We can reproduce the given crash. In the previous studies, it has been shown that EvoCrash is the best performed approach in terms of crash reproduction. But the problem with that study, or it's not a problem actually, but the number of crashes that they use for the comparison is 54, and 46 of them are reproduced by EvoCrash. So we cannot really see the limitations. It cannot reveal the limitations of this technique. So in this study, we wanted to find the challenges that we have here in the search-based crash reproduction. So we needed a new benchmark, and we defined 4 requirements for this benchmark. All of the projects in this benchmark should be openly available. It should be under active maintenance. All of the stack traces and all of the bugs should be linked to a buggy version, and we should have a diversity in the size of the project. When we look at the existing benchmarks, like DefectSforge and SF110, they cannot fulfill all of those requirements. And for that reason, we designed our own benchmark called JCRASHPACK. JCRASHPACK contains 200 crashes, and most of the crashes are coming from a complex project like XWiki or Elasticsearch. Also, we looked at the DefectSforge and we found all of the crashes, only crashes that we have stack traces, and they're not assertion failures, for instance. It's only the crashes like a null pointer exception. But when we look at the information about this benchmark, we can see that the projects used in this benchmark are diverse. So XWiki and Elasticsearch are quite more complex than the other ones. Also, we can see the diversity in the type of the exceptions, as we can see in this table. Also, we developed and used an open source experiment runner called XRunner that can gets the crash reproduction tools and run them in parallel on all of the 200 crashes of JCRASHPACK, and then it will give us some information about the success rate of the approach and the execution log and generate the test case. With all of with the benchmark and with the XRunner, we performed our empirical evaluation. We only applied EvoCrash on those crashes because the other tools are not available openly. We ran them on all of the crashes, 200 crashes. We ran EvoCrash, we repeated each execution 10 times because of the randomness in the genetic algorithm. And we've set the 15 minutes time budget for the search process of EvoCrash. And with the results of these runs, we wanted to answer 3 research questions. The first research question is about the performance of the EvoCrash on reproducing those crashes. The second research question is about the effect of types of the projects and crashes in the performance of EvoCrash. And finally, we wanted to see what kind of challenges we have there in our unsuccessful executions. I cannot show all of the results here, but I'm just going to show some highlights. The first thing that we saw is that most of the crashes cannot be reproduced with EvoCrash at all. So only 87 out of 200 crashes can be reproduced by this tool. Also, when we look at the crashes in different projects, we can see that lots of crashes cannot be reproduced in the more complex projects like XWiki and Elasticsearch. So we wanted to see why, what kind of challenges we have those not reproduced crashes. So we performed the manual analysis in all of the unsuccessful executions, and we categorized our challenges to 13 challenges. Some of these challenges are coming from the general search-based test generation issues. For instance, input data generation. You usually need a complex input for the test, and well, it's hard to generate that. But some of them are dedicated to search-based crash reproduction itself. For instance, if you have an exception in the try catch and it's captured and it's reported via an execution log, then Evo crash cannot detect that if a generated test case can reproduce the crash or not. Finally, the replication package is openly available in Zenodo. And the other thing is that after this study, now that we knew the challenges, we wanted to improve this process. So first, we made a tool called Botsing. It's a framework for search-based crash reproduction. It's well tested and it's under active maintenance. And also, we are continuously adding new features to improve the results that we saw in the JCRASHPACK. For instance, for addressing the complex input generation, we introduced behavioral model seeding, which is another study, and it's published in STVR, it's Software Testing Verification and Reliability Journal, and it's open access, so it's available as well. And yes, thank you very much for listening. Botsing is an open source tool, and it's open to contribution, and also we have another repository for the demo, so you can just try it. Thank you very much, and I would be happy to answer your questions.
All right, thank you for the presentation. Yeah, I have a question. So I wonder that how did you verify the success of reproduction? Because there could be different types of crashes, whereas you can produce one, so your tool can produce a crash, which is different from the ground truth.
So Botsing or Evo crash in general, it gets in a stack trace and it generates a test case, right? So if you execute that test case and it can throw exactly the same stack trace as the given one, then we count it as a success.
Okay, thank you. My second question is that you are talking about crashes. So I wonder that whether these tools could also be able to handle non-crash failures, and what would be the challenges if we want to extend it to, to reproduce those non-crash failures?
Well, since it's a search-based algorithm, the only thing that we need is a fitness function or multiple fitness functions, multiple search objectives. If we have any objective there and we can map it to a fitness function, this is the only difficulty. And then with that, we can hope that a new tool can reproduce other scenarios as well. For instance, it's another study that it's the tool name is Catcher, and there it tried to find a potential bugs there and then try to reproduce those potential scenarios which leads to the potential bugs and see with dynamic analysis that if we have a bug there or not. But yes,
okay.
There are some other studies to do that as well. Yes.
All right, great. Thank you for answering my question. All right, let's thank the speaker. All right, so now let's move to the next talk, which is a technical paper, an investigation of cross-project learning in online just-in-time software defect prediction, presented by Linzhuo Minku.
Okay, hello everyone. My name is Leandro Minco, and I'm going to present an investigation of cross-project learning in online just-in-time software defect prediction. And Sadia Tabassum is also here with us. Just-in-time software defect prediction, or JIT-SDP, consists in predicting whether software changes are defect-inducing or clean based on features describing such changes. What people usually do is to adopt machine learning algorithms to build JIT-SDP models based on previous within-project changes that are known to be defect-inducing or clean. But the problem of doing that is that in the beginning of software projects, we don't really have that many within project data available to build well-performing JIT SDP models. So in order to overcome this issue, people have investigated the use of cross-project data. And they found that models created using only cross-project data have achieved similar predictive performance to within project models. However, the existing work on cross-project data assumes that we never really receive new within project or cross-project training examples over time. When in reality, JIT SDP is actually an online learning problem where additional within project data is received over time and can potentially be used to improve the predictive models. So the role of cross-project training data is unclear in realistic online learning scenarios where we are actually receiving additional within project training examples over time. It could be that cross-project training data are helpful only at the very early stages of the software project when we have very little within project data, and then afterwards it becomes decremental. Or it could be that cross-project data are helpful for prolonged periods of time, potentially improving predictive performance over within project models. And this may be really the case, especially considering that this is a class imbalance learning problem that may suffer from concept drifts. These concept drifts are variations in the defect generating process that may hinder the predictive performance of the JIT SDP models over time. So the aim of the study is to investigate if and to what extent cross-project training data are helpful in realistic online learning scenarios. To perform this investigation, we've used online JIT SDP models that fully respect the chronology of the data, both in terms of the commit time, which is the moment when we want to predict a software change, and the labeling time, which is the moment where we can label a software change, producing a training example to update our predictive models. In particular, we used a within project approach that receives additional within project training data over time and use this additional training data to update the predictive model. And we used cross-project approach where both cross-project and within project training data arrive over time. We've developed 3 different cross-project approaches. The first one is an all-in-one approach where both the cross-project and the within project data are used together to train a single predictive model. The other one is a filtering approach where the cross-project data is filtered based on their similarity to recent within project chains. And the last one is an ensemble approach where different predictive models are trained with data from each project. The first research question answered in our work is, can cross-project data help to improve predictive performance in the initial phase of a software project when there is little within project data available? For how long and to what extent? This table here shows the G-means obtained by all the approaches involved in the study, both using OB as one possible base learner and ORB, which is another possible base learner. The G-means are the geometric means between the recall on the defect inducing and the clean class. And here we can see the G-means for 10 different open source software projects. In this last row here, we have the ranking of this approach in terms of G-means across projects. And we can see here, basically, in summary, that the all-in-one and the filtering approach are better ranked than the other approach. And the within project approach actually obtained the worst rank. The effect size for individual data sets were typically large, and the G-means were up to 53.9% higher for the cross-project approach. The initial period where the within project data is typically not enough to produce well-performing within project models varied from 461 to more than 6,000 commits. So it's a considerable period of time. Our second research question is, can cross-project data help to prevent sudden drops in predictive performance, which may be caused by concept drift? To what extent? And here I show some sample results. Basically, what we observed is that we can see some severe drops in the G-mean for the within project approach, which is showing black in these plots over time. whereas the cross-project approach managed to reduce these drops, or in some case even eliminate these plots, these drops. So we can see here the cross-project approach showing other colors than black, right? Our third research question was, what is the overall effect of using cross-project and within-project data together on the predictive performance throughout the development of software projects? So all the way from the beginning to the end. And what we observed basically was that filtering and the all-in-one approach were again better ranked than other approach. And this was both in terms of the G-means and in terms of the individual recalls on the clean and on the defect-inducing class. The improvements in G-mean were of up to 16.88% for the cross-project approach, and the effect size were again typically large. Now, this is an interesting result because in the offline learning literature, which ignores concept drift and that initial period, cross-project data led to similar rather than better results than within project models. And here we could show that the cross-project data used together with within project data can improve the predictive performance over within project models. We've also collected 3 proprietary repositories from a Chinese software development company for this study. And we found similar results in the sense that the all-in-one and the filtering approach were best ranked than the within project approach. Now, one interesting thing to note here is that the open source data used together with the proprietary data as cross-project data helped to improve the predictions on the proprietary data. So this is one of the things in our study that suggests that the amount and variety of training data is important for JAT-SDP models. But it's worth mentioning that having a good number of within project training examples was still important, both for the open source and for the proprietary predictions. So in conclusion, we performed the first study of cross-project learning for JAT-SDP in a realistic online learning scenario using both open source and proprietary data. The all-in-one and the filtering approach can prevent very low predictive performance at the initial phase of the software project. The cross-project data can help to reduce or eliminate drops in predictive performance that may be caused by concept drift. And the all-in-one and filtering approach can improve the overall predictive performance compared to within project learning. We found that the amount of both within project and cross-project training data was important. Thank you.
Thank you for the presentation. We have a question from the audience. You indicate you maintain chronology. How do you deal with merged branches which may have been developed in parallel and have no natural chronology?
Oh, okay, that's a good question. So in this specific study, we are not really distinguishing merged branch from other types of chains. So we use the commit guru tool to extract the data for our study. Yeah, so, but it's a good point, actually. Actually, this is one of the points in just-in-time software defect prediction that needs to be further investigated, right?
Okay, thank you for the answer. I have another question. So for your RQ3, you just reported the recall of the results. So I wonder that's why precision is not needed.
So we reported the G-means. The G-means are basically the geometric means between the recall on the clean and the defect-inducing class. So we are considering here the performance metrics that are the most adequate for class imbalance problems. Precision is not really adequate for class imbalance problems because it's affected by class imbalance. So depending on the level of class imbalance that you have in your problem, you may look like you are getting a better result or a worse result just because of that level of class imbalance. The recall on each one of the classes separately will not really have this problem.
Okay, Thank you for answering my question. And again, thank you for the presentation. So now let's move to the last talk. It is a journal first paper, and the title is an empirical study of the long duration of continuous integration builds, presented by Taylor. We cannot hear you.
Hello, everyone. I am Tahir Galib. In this talk, I'm going to present our work with Daniel and my professor, Jenny Zhu. It's a study on the long duration of continuous integration builds. So first, what is continuous integration, or CI? So continuous integration is a software practice that allows developers to integrate their code into shared repositories and allow them to run and compile their code on a common infrastructure, and then get early feedback from CI on their builds. CI goes through like a number of phases. First, it starts with developer changing the code, pushing the code to a common repository like GitHub repositories, and then those commits will trigger a build on a CI service like Travis CI. And if things go successfully, the project is packaged and deployed to a deployment provider. However, a build generation may take too long, which might impede developers from engaging in other development activities and consumes lots of resources and energy. And sometimes developers may require to exclude the tests from the project to speed up the builds. And sometimes they might give up using CI altogether. Therefore, in our study, we investigate why builds might take too long to generate. So first, we study the proportion and frequency of long build durations, and then we model long build durations to understand the factors behind long build durations. So we took a Travis torrent that has over 1,000 projects, and then we took only projects that have build duration deviation of 10 minutes, which means they have the problem of long build durations, to come up with 67 projects that suffer from such a problem. And then from these projects, we study the proportion and frequency of long build durations. Then we classify builds into short and long using 3 thresholds, and then collect 28 code and CI metrics across 3 dimensions, and build mixed effects regression models to understand the factors that are associated with long build durations. So first, we found that 40% of builds take over half an hour to generate, with an overall median of 20 minutes, and only 16% that takes less than 10 minutes, which is the acceptable build time based on the developers' feedback. So second, build durations do not always increase linearly over time as we expect. So they don't go linearly, but rather we found that there is lots of fluctuation as we see here in this project. Another thing is that we found that past builds that actually go through all the build phases, they might take like less time than failed builds. And when we investigate this problem, we found that the cause of this is tests that take too long to run, or rerunning failed commands multiple times. So building our regression model gave us a high performance on predicting and modeling long build durations with an 87% AUC. And in addition to that, we found that in addition to the common wisdom factors that really affect build durations, like project size, density, and number of jobs, we also found that CI practices and configurations can be really associated with long build durations. For example, we found this practice that developers may try to maintain successful builds to avoid build failures, but that practice actually delay the generation of software builds. For example, developers might increase the waiting time for commands or tests, or keep retrying running the commands multiple times to avoid build failures. But however, we found that these practices only give 3% reduction of build failures while increasing the number of long lead generated builds. We also found that enabling the fast finish feature in CI is associated with the long with fast generation of builds. So they allow failures jobs, as we see here, that do not actually affect the build status, and using the fast finish will not wait for these jobs. And we found that this practice is only used in 50% of the projects in our study. We also found that caching has a strong association with short build durations, with faster builds. So caching allows actually the CI building machine to install, for example, dependencies from sources and upload them to the cache server. And then next time when the build is generated again and again, the binary files of these dependencies will be just downloaded from the cache server. So we found that 2/3 of the projects in our study adopt this caching feature of CI, but only like 1/3 of them, they got benefit from this. And when we investigated, we found that it's actually a misuse of the caching feature in these projects. So yeah, we also found that the builds can be faster on weekends and at night, and that's because the over workload on the CI servers. So let's take these take-home messages for developers, that they do not need to remove builds, tests, but rather optimize, and not all build jobs run in parallel. And CI practices and misuse can affect build durations in addition to the CI workload. And here is a summary of the key points of our study, and more details can be found in our MC paper. Thank you.
Okay, so thank you for the presentation. I have one question. So do you think that applying some of the regression testing techniques like test prioritization, minimization may potentially reduce the build durations?
Right, yeah, of course. Actually, that's what I meant by optimizing builds. It's by other test selection, using test selection techniques or test prioritization techniques. But actually, we found that projects also do not adopt these practices. And there are studies in this, actually, the impact of tests on long build durations. And we also found that like developers try to select and prioritize tests rather than build jobs, because the build can have multiple jobs. So they don't also consider prioritizing their jobs and their and selecting the appropriate like runtime environments as build jobs. And focusing only on tests won't help, because like they're not actually using the features provided by the CI services. And that's like one of the main observations in our study, is that they don't use CI features like well.
Okay, thank you for the answer. All right, I don't think we have enough time for more questions. All right, so thank you all for attending the session on testing and debugging. And again, I want to thank all speakers, and I hope you stay here and enjoy the rest of the sessions. Thank you.
24 on testing and debugging. I'm Yijun Yu from the Open University in the United Kingdom. Today we have 7 talks. So let me first introduce Tajuan Byam from University of Minnesota to answer your questions after showing his video. Yeah, let's show the video first.
Hello, I'm Taejun Byun, a PhD student from University of Adoption of AI. Hello, I'm Taejun Byun, a PhD student from University of Minnesota. I'm going to present our work on a new concept for the assurance of machine learning systems. As machine learning is infiltrating into safety-critical systems, it is becoming a software engineering problem. However, the quality assurance techniques are not catching up fast enough with the disruptive adoption of AI. For example, Zipline flies autonomous drones to deliver medical supplies, and they allegedly spend more than 50% of their time and money in verification and validation. I believe that one possible way of tackling this problem is to adopt proven concepts for autonomous systems. And specifically, I will talk about model-based engineering. Model-driven software engineering is a popular concept that is widely adopted successfully in cyber-physical domain. It argues that we can create various models which capture the abstract representation of the knowledge and activities for a given task and harness this throughout the development lifecycle. It is used for analysis, verification, testing, assurance, and so on. What if you want to apply this concept for learning tasks? What would it look like? Let's take digit classification as an example. The MNIST dataset comes with 60,000 handwritten digit samples, and if you can introduce human relatable variables for explaining the whole dataset, such as the class label, the size of the digit, the shape, the thickness, and so on, we can possibly explain the whole dataset with this abstract representation. Once this is done, we can measure the adequacy of a test weight against the semantic model that we just constructed, or we can even construct test cases anew from this model that we have, if we have the generated capability. So we ask ourselves this question: can we construct this domain model? And the answer is yes, and it can be done automatically using manifold learning. Manifold learning tries to uncover and analyze the hidden low-dimensional data embedding structure behind the high-dimensional dataset. It relies on model manifold hypothesis, and what that means is that the valid data is actually lying in a topological space that is much smaller than the input space. In this work, we use variation autoencoder for learning the manifold, which is an unsupervised learning technique for obtaining a latent variable generative model. It is composed of 2 neural networks, a probabilistic encoder and the decoder, joined together by a bottleneck which forces all the information relevant for reconstruction to be compressed. As you can see in the figure, all the digit samples are nicely encoded in this compact 2-dimensional space, and different classes are separated naturally and nicely without any supervision. So it finally gives me that compact representation along with the encoder and the decoder, which maps the data to and from this manifold. With this variation autoencoder, the first idea we experimented is the test adequacy measurement. We took the encoder part and the manifold and sliced the manifold into n bins of equal data density per each dimension. For coverage measurement, we check how many of these bins have one or more encoded samples. So we trained a VAE for MNIST and ran the EMNIST dataset as a test suite for evaluation. We first divided the test suite by class and measured the coverage. We then measured the correlation of the coverage obligation to the class label as a representative semantic feature. The result shows that the manifold coverage has a stronger correlation to class labels than neuron coverage or neuron boundary coverage. Another idea that we propose is generating novel fault-finding test cases from the manifold. We use conditional VAE, which learns manifold per class label, so that we can specify the label upfront when generating test cases. Novel test cases can be sampled from this manifold and run on the model under test to find the faults in the model. This framework can quickly generate lots of realistic yet fault-revealing test cases, like shown in this figure. We developed this idea further, and it will be presented in AI Test 2020. So here is a one-slide takeaway. Manifold enables model-based software engineering for learning-enabled systems, and the independence that it provides is valuable for assurance tasks. For concrete instantiation of this idea, we propose a test adequacy measurement and a test case generation technique. The preliminary experiments show that the proposed approaches are viable and effective. I believe that this manifold can be harnessed in other different ways as well, and we are continuing the exploration. Thank you for your time and attention, and please feel free to contact me.
Hello, everyone.
Hi. Yeah, I don't see a question in the shared window, but I do have a question for you, Tayo. When you say this approach help with the testing by dimension reduction, do you lose some accuracy because of that?
Yes, there certainly is a precision trade-off when you're trying to compress too much into this embedding space. But this embedding space is something you have a heavy handle. I mean, for the complexity of the data, you can have a larger dimension for the latent space or smaller. So the smaller it is, it's more compact and easier to handle for computation, but you lose precision. But there's a good balance, I think.
Great. And can you give more examples of its applicability to different areas?
Yeah, for sure. So it can extend to other types of machine learning models, because in machine learning, this representation learning is so universal a concept that is being used everywhere. Like for sequence modeling, for language generation, there are all embedding spaces. So if we develop techniques that harness this embedding space for assurance techniques, I think it can generalize to many other machine learning systems.
Okay, thank you. The next speaker we have is Cody Watson from Washington and Lee University. His first talk will be on learning meaningful assert statements for unit test cases. Now the floor is yours, Cody. You need to unmute. Yeah, off you go.
Hi, my name is Cody Watson, and I'm here to present on learning meaningful assert statements for unit test cases. As software engineers, I don't need to convince you the importance of software testing, and software testing happens to be one of the most expensive phases of the software lifecycle. Our work focuses on unit testing, which provides a fundamental basis for testing that integration, system, and acceptance testing can be based upon. Currently, there are two tools that are used to provide these test suites and the test methods with their associated assert statements. The first is intelligent feedback directed generation tool called RANDUP, where they generate a sequence of method invocations for the class under test and try to provide an assert statement that captures the behavior of the program. The second tool is EvoSuite, which is a mutation-based generation technique. And this technique tries to mutate the focal method under test and attempts to generate an assert statement that captures that mutation. So our work focuses on the improvement of these tools in some regard, because analysis of these tools on real-world faults shows a lackluster performance in their ability to detect faults. And it has nothing to do with the generated test method itself, but primarily focuses on the weakness that they're unable to generate complex and meaningful assert statements. So we believe that by introducing a learning-based approach, we can supplement these tools better. And this is best shown through an example. So let's look at this test method. As you can see, there's a sequence of method invocations that can be fairly complex. Our technique attempts to generate the highlighted portion here, which is the assert statement that correlates best with the test method and the focal method under test. And we implement neural machine translation, which is a technique we use to generate these assert statements. As an overview, we generate test methods with their focal method sequences. We then subject them to a series of neural networks. And finally, we're able to generate newly translated assert sequences. So let's take a little bit of an in-depth look at our neural machine translation model. It's comprised of three basic parts. The encoder, which, as you can see as an example here, is taking a series of characters and translating them into a new language. In our case, we're taking a sequence of source code tokens and translating them into a new assert statement. The encoder will take these characters and translate them into a latent representation. The attention mechanism associated with this will then determine what part of the encoding sequence is most pertinent for the decoding sequence. As you can see here, the weight of E3 is the most important part of the encoding sequence for the decoding of token D4. And then our decoder here takes the information from the encoder, the information from the attention mechanism, and any previously decoded tokens in order to decode the token at the current time step. And we wrap our approach around this basic model of neural machine translation. Our approach named ATLAS, or Automatic Learning of Assert Statements, has 5 primary steps. The first is test method mining, where we go to GitHub and we mine many test methods written by developers with their associated assert statements. The second step is the identification of the focal method, where we're trying to identify the method that the test method is focused on. Our third step is the test method assert statement pairing, where we attempt to separate out the assert statement from the test method and focal method context, and we'll use that as our training examples for our neural machine translation model. Our fourth step takes a raw and abstracted data set and attempts to see which one the model learns best from. And our fifth and final step is the actual training of our neural machine translation model. So our first step is the focal method identification. Let's take this example test method. In this example test method, we first identify the assert statement, and our first step is to identify the method invocation that is in closest proximity to that assert statement. Here we find that method is empty. However, if isEmpty did not exist, we would find the previous closest method invocation to the assert statement, in this case, find by target collection UID. Once we've identified the focal method, we then extract the literals, identifiers, operators, and constants associated with that focal method, meaning that we leave all structural information and language keywords behind. We then append this context to the end of our test method. This provides enough information for the neural machine translation model to generate an appropriate assert statement. Our last step is to extract the actual assert statement away from the test method, replacing it with an assert placeholder token. This comprises of our test method assert statement pair, or what we refer to in our paper as a tap. We then use this information as input data for our training for our neural machine translation model. So after training of our model, we then look to analyze some of the results. And our first research question asks, is Atlas, our approach, able to generate assert statements resembling those manually written by developers? And we find that both in the raw data set and in the abstracted data set that we analyzed, we are able to get a relatively high amount of perfect predictions. In the raw data set, we're able to perfectly predict over 17%, in the abstracted over 31%. Now, what perfect prediction means is that we're able to predict exactly what the developer had written for the given test method and focal method context. We wanted to extend this with a mechanism called beam search. And beam search allows us to generate a number of different assert statements for a given test method and focal method context. We found that with a beam size of 10, meaning we generate almost 10 assert statements we generate exactly 10 assert statements for the given test method and focal method context, we see an improvement in the perfect prediction rate of over 20% for the abstracted data set, resulting in a perfect prediction rate of 55.73%. Even in the raw data set, we saw an increase of over 7% from only generating one assert statement in the previous step. We also chose 10 because we felt that we weren't overburdening the developer with having to choose from a long list of assert statements to determine which one appropriately fit the test method and focal method. We also didn't want to just look at perfect predictions. We also wanted to look at the imperfect predictions of the model. And we found that by only changing one token in the imperfect predictions, meaning that the prediction itself was not exactly what the developer had written, by only changing one of those tokens, we can see an improvement of 23.62% of the imperfect assert statements into perfect assert statements. We also found that 10% of the imperfect predictions can represent a valuable and correct assert statement, meaning that our model can provide some orthogonal results to what the developers had chosen to be the assert statement. And in the figure, you can see a distribution of the number of edit operations it would take to translate our imperfect assert statements into perfect assert statements. The last research question I want to talk to you about is the types of assert statements we're able to predict. And this is important because we want to have a model that generates a variety of assert statements and is capable of generating those assert statements for the particular test and focal method at hand. In the red bars, you can see the total asserts in our testing data set, and in the tan column, you can see the perfectly predicted assert statements for that given type. And you can see even for our least represented assert statement, assert array equals, we are still able to perfectly predict almost a third of those assert statements. So in conclusion, we generated an approach called Atlas to be able to use neural machine translation to generate complex assert statements that resemble what developers have written. we created our test set out of TAPs, or test method assert statement pairs, that incorporate the focal method context. And we showed that our approach Atlas is able to generate meaningful assert statements that resemble what developers have written. And more information can be seen on our website. Thank you.
Great. Let me bring your attention to a question in the audience. When you do the comparison with the related work, have you compared the generated assertions of the test with those generated by the two Randup and Evil Suite?
This is a great question. And in fact, we were not able to for a number of different reasons. The first reason is primarily because the approach itself generates the test method. So they have a distinct advantage in the ability to create a test method and then an assert statement that is specifically targeted at that test method and focal method statement. With our approach, we're able to take any test method that the developer has written and generate an appropriate assert statement. It could be a future next step to compare against these approaches, but there are some discrepancies that don't allow for a fair comparison between the two tools, or three tools, I guess, in this case.
Yeah, there's a second question from Jens Krinko. The idea LCBA performs badly, and the example in your presentation does not point to the focal method. Aren't you encoding the assertion statement itself into the query?
So yes, to train our tool, we are incorporating some information from the assert statement, which is a slight limitation of the approach. We do feel that any developer, any reasonable developer, would have access to the focal method that they would want to test, and therefore would be able to provide some of the important context to use our tool. And therefore, we don't feel that this is a significant limitation in our ability to generate assert statements that would represent both the test method and the focal method under test.
Yeah, there's another question in the audience. Without considering the structure of the code, it seems that you are not considering, you are only considering tokens in the code. How can you claim the generation of complex inputs?
Yes, so we do not incorporate the structure of the code because when we initially did provide the structure, the neural machine translation model was confused by all of the structural components. We also found that when looking at assert statements, frequently the assert statement does not require any structure from the focal method. It only requires the tokens within the test method or within the focal method to obtain the context necessary in order to generate a meaningful assert statement. And we were able to generate many meaningful and complex assert statements. And if you go to our website, you'll see a list of the number of assert statements we were able to generate.
Great. I think the time is up, although there could be more interesting questions. And your talk again, so we can ask them later. Thanks.
Thank you.
Let's switch to next speaker, Guanhong Tao from Purdue University. His talk is on trace divergence analysis and embedding regulations for debugging recurrent neural networks. Are you ready? Yes, please go ahead.
Thanks for the introduction. Hello, everyone. I'm Guanhong from Purdue University. I'm going to present our paper, Trace Divergence Analysis and Embedding Regulation for Debugging Recurrent Neural Networks. This is a joint work from Purdue University and Rutgers University. In software engineering, we have a lot of artifacts that are in the form of text or sequences, such as code comments, user reviews. We utilize those artifacts to assist software development or maintenance. Recurrent neural networks are widely used machine learning models that can deal with those inputs. Here is an example. Send strength is a tool using machine learning models to predict sentiments. A follow-up work utilizes this tool to extract problematic API features based on negative sentiment predictions. However, a recent study shows that sentence strength has very low performance on negative sentences, which can negatively impact the downstream applications. Hence, in this paper, we aim to debug R models for better performance. A typical textual application usually takes in a text sequence and produces a desired output. Text sequence consists of a list of words, which are first transformed to word embeddings before fed to an R model. Existing studies show that word embeddings are a dominating factor for performance of R models. Different embeddings can lead to significantly different accuracy, from 63% to 89% with the same model. We hence focus on fixing bugs caused by problematic word embeddings in this work. Neighboring words can be used to measure the quality of word embeddings. For a target word error, we list its neighboring words using the original embeddings. We can see that word correct is very close to word error, which is not desired when it comes to sentiment analysis applications. The regulated column shows the results of regulated embeddings. We can see that word correct goes down on the list. Here is another example. The target word is reinstall. Our regulated embeddings move related word install up on the list. Although embeddings seem external to the model itself cannot be studied separately without considering embeddings. As such, we treat them as a whole during bug fixing. Suppose we try to debug an R model whose code implementation is in the following. The task of this code is to produce some label given an input sentence. There is a loop in the code. We show the R model on the right and also unroll the loop to individual steps. Each step computes the equations in the box, which are mathematical representations of line 8 and line 9. XT is a word embedding, HT is a history vector, and OT is an output at each step. We say each pair of input, including internal and output, is a state, and all those states constitute a trace. The last output is the final prediction. Line 6 maps individual words to their corresponding embeddings. A misclassification is due to some buggy internal states in a trace. We use an example sentence to explain our analysis. Word also is first transformed to its embedding and then fed to the model, which produces an output for current step. The input, history, and output constitute the state vector. It is the same for the next word and the following. Those states along the time step compose a trace. We collect those state vectors as inputs and outputs, and then train classifiers on validation set to identify divergent steps. Please find the details of constructing those classifiers in our paper. Here are the output traces produced by the classifiers along the time step. We can see the two traces diverge at word merge, which means the state is problematic at this time step. Problematic state dimensions are the root cause of buggy states, which leads to misclassification. We aim to identify and fix those dimensions. We use the same example from previous slides. For a divergent step, we first obtain its state vector, and then we times it with a pre-trained importance factor. Those dimensions with large values are the defective dimensions of buggy states, because they are more important to the classification results. Finally, we aggregate the defective dimensions from all the divergent steps. From our previous analysis, we know that the presence of misclassification is due to the sensitivity of model on defective dimensions. We hence aim to reduce such a sensitivity by regulating word embeddings. We've identified defect dimensions in the previous slide. Here, we add random perturbations on those dimensions. Now, we have an original state vector and a perturbed version. Different from traditional training procedure, we freeze model parameters. We use the output difference from two sets of state vectors to regulate embeddings. Finally, we retrain the model using regulated word embeddings. Please find details in algorithm 2 in our paper. We evaluate our technique trader on 135 models and can improve model accuracy for 5.37% on average. We also conduct a case study on model behaviors. Red color denotes negative sentiment, green denotes neutral, and blue denotes positive. The ground truth is on the left. The right part shows two example sentences. The sentences in the top rows are produced by the original model, and the bottom rows by the fixed model. We can see that the fixed model can produce negative sentiment of word work in presence of word not, whereas the original model cannot. Our artifacts are available on GitHub. Our technique is related to other existing model debugging work. Due to time limit, I will skip this. Please see our paper for detailed discussion. Thank you. I'm happy to answer any questions now.
Yijun, we have no sound from you.
Hello? Oh, great. Yeah, my question, let me make it briefer. So you mentioned that you treat the word embedding and the training as a black box and tune the regulated word embedding together. Would that change the performance when you change the data set? Because word embedding is pre-computed, I guess.
Actually, we are not treating the model as a black box. We're actually using each step in the R model to try to compose the input and output at each step, and use this data during the on the evaluation set to train another classifier to try to find the difference between the correct prediction and the incorrect prediction. And we use this information to guide the search on the embedding part, because the embedding usually are pre-trained on a large data set, but those data sets are usually like a Wikipedia or Google News, this kind of data, which is not very similar to the data set usually used on like a specific task, like in the sentiment analysis task I mentioned. So we used use the information of the current data set to adjust the existing embeddings, so we can like have better performance on the current data set. So yeah, does that answer your question?
Yeah, sure. Just try to confirm, after the regulating the embedding, will you use the adjusted model to another project or another task, or you consider the improvement has been done?
So currently we are using the embeddings just for the current data set. So after the regulated embedding, it's still use the same task in the data set. Yeah.
Okay, all right. Thank you for the speech. I don't have another question in the audience, so we'll try to switch to the next talk. So the next one is, again, Cody. So Cody will show us a video and then explaining the idea behind his tools called deep mutation. Yeah. Cody, you can hit the play button now.
Hello, my name is Cody Watson, and in this video I will be demonstrating how to use deep mutation, a neural mutation tool. Deep mutation is based on the idea that the perfect mutant is the buggy version of some piece of code, and mutation operators should be inspired by real bugs and developers' changes. We know that a bug fix implies a developer has transformed buggy code into its fixed code. Therefore, mutation should occur by taking that code in the reverse direction. What we mean by this is taking fixed code and transforming it back into its previous buggy version. Deep mutation relies on a machine translation model that was trained on thousands of these real-world bug fixes to translate fixed code into its buggy version. Here we provide a quick overview of our approach. Methods are extracted from the system, abstracted to reduce vocabulary and maintain a good representation, mutated to generate the appropriate mutants, translated back into raw source code, then compiled and tested in the system for which they were designed. Here we show deep mutation's GitHub repository, which contains the source code and environment that deep mutation needs to properly execute. For convenience, we've already downloaded the tool onto our machine, and we'll also run our environment script to ensure that all environmental components are properly installed. Before running deep mutation, the user should examine the configuration file to determine the proper paths and other parameters are set correctly. In particular, the number of beams for beam search can be set to generate multiple mutants for the same method of source code. Now we can run the deep mutation tool. For this video, we'll speed up this process. Now we can analyze the output folder, where we can see a number of important files. Methods.key contains the signatures of the original methods, methods.src contains the original source code of those methods, and methods.abs contains the abstracted version of those methods. The same type of files are generated for the newly created mutants. The only difference worth noting here is that mutants.src contains the translated mutants back into raw source code from their abstracted version. The mutant folder contains all the important information about the generated mutants. For example, the highlighted file is the original class of the system where the mutant was injected. Moving to that mutants directory, we can see the original version of that method, the changed version, or the mutant, and the list of operations to get there. We can see that in this mutant, deep mutation deleted this line in addition to swapping column index with column key. Thank you.
Yeah, thank you. We don't have a question from the audience. Let me just ask you a quick question about this tool. Do you try this tool on various programming language, or is it specific to Java?
That's a great question. We do only use Java as the language, and one of the big reasons for that is because of the software used to extract the changes from GitHub. We use Spoon, which was primarily generated for the Java language, but a good future step in this research would be to apply it to a variety of different languages, which would require retraining of the model most likely.
Okay, brilliant. Okay, thanks for the speech. The next talk is already shown on the shared screen. It will be given by Claudio Manghi from the University of Luxembourg. His talk will be about ambiguity and specification patterns for robotics missions. Yeah, the floor is yours, Claudio.
Thank you for the introduction. This work is titled Specification Patterns for Robotic Missions. I'm Claudio Menghi. This work has been developed in collaboration with Christo Tsiganos, Patrizio Pelliccione, Carlo Ghezzi, and Thorsten Berger. Let's start with the problem definition. So the robotic market is currently subject to a radical change. Robots were usually in classical robotic applications, single purpose. They were able to perform a single task and usually deploy within industrial facility. On the other hand, robots are now becoming general purpose. They are able to perform many different tasks, and they are usually deployed within end user houses. For this reason, the problem of defining the goal of the robotic application is slowly moving from the hands of highly qualified expertise that have programming capabilities and a deep knowledge of the robotic domain to the hands of inexperienced users that do not have this background. The mission, or with the term mission and or mission requirement, we refer to the high-level goal the robotic application has to achieve. After the user have identified the mission requirement, he or she has to transform the mission requirement to a mission specification. The mission specification is a lower level representation of the requirement, usually provided in terms of some programming language, such as C or Java, or some logical-based language like LTL or CTL. Transforming the high-level mission requirements into the lower-level mission specification is called mission specification problem. And solving this problem is generally difficult. As a software engineers, one of our goals is to provide systematic procedures that help robotic developers and end user in defining the mission requirements and translating the mission requirement into a mission specification. That is, in solving the mission specification problem. This is the goal of this work. To solve this problem, we had proposed a catalog of mission specification patterns. Essentially, a pattern is a template solution for a current problem, in this case, a mission specification problem. It essentially maps a high-level recurrent requirement into a specification, in our case, LTL or CTL. Here is the catalog of our pattern system. It contains 22 mission specification patterns, which are represented within the gray boxes. Essentially, we have three categories of patterns. The core movement patterns that specify how the robots move within their environment, like the robot should visit like several locations. Then there are some avoidance patterns that specify constraints on the robot, like the robot shouldn't hit object or something like this. And then we have trigger patterns that specify robot reactive behaviors based on stimuli, like if there is a user, the robot should help the user, or like this type of requirements. So this is an example of a pattern, is an example of strict order patrolling pattern. As you can see from the slides, a pattern has a name, which is the unique identifier of the pattern. Then there is an intent, which provides and describes the mission specification problem the pattern aim at solving. Then there is a template specification. In this case, LTL. We have also specification in CTL, but ideally user can also provide specification in other languages. Then there are variation of the pattern that describes likely change that can be applied to the pattern, example and known users that specify how to use the pattern, relationship with other patterns, and occurrences of the pattern in the literature. To support the use of our pattern catalog, we have developed a tool which is called PSALM, Pattern-Based Mission Specify. Essentially, the tool provides a graphical user interface that provides a structured English grammar that the user can use to specify the mission requirement. Then the tool automatically translates this mission requirement to mission specification, in our case CTL and LTL, using the syntax of well-known tool presented in the literature. The tool is available on our website, roboticpatterns.com. To evaluate our contribution, we had considered to what extent are mission requirements expressible using our pattern catalog, to what extent are mission specification expressible using our pattern catalog, and does our pattern catalog support the formulation of mission requirements and specification in a set of real-world scenarios. So the answer to research question 1 is that in 84% of the cases, the mission requirements were expressible using our pattern catalog. Then the answer to research question 2 is that in 92% of the cases, the mission specification were expressible using our pattern catalog. This is a reasonable coverage for a pattern catalog. However, we added 3 additional patterns to cover the cases that were not supported by the pattern. So the answer to research question 3 is that the pattern catalog support the creation of mission requirements and specification in 5 real-world robotic application scenarios. Here is an example. This video has been recorded within the facility of Parrobotic, one of our industrial partners. Essentially, the robot is patrolling a set of locations. When it detects that there is a user that needs help for carrying the object, it helps the user in carrying the object. And then the patrolling activity restarts. The mission requirement was specified using our tool. The mission specification was automatically generated and then sent to a mission planner and finally executed on the robot. So to conclude, we have defined a set of specification patterns for robotic mission. We have implemented a tool that supports the usage of our pattern, and we evaluated our pattern on real and simulated scenarios. So everything you have seen in this presentation The tool, replication patterns, is available on our website, roboticpatterns.com. Thank you for the attention.
Yeah, Claudio, there's one question from the audience. It's a nice talk. Can you explain the experiment setup for the research question 1 and 2?
Yes, for the research question 1 and 2, we relied on specification that we collected from the research literature. So for research question 1, we had like, around 300 mission requirements that we had found within existing tools, and then we check whether we were able to express those requirements. And then to complement those results, then we had performed the experiments on real world scenarios.
Thank you. Now we have to switch to the next talk about the ProxRay. This is going to be, yeah, also from a journal first talk. Oh, are you muted?
Hi, everyone. My name is Farhan Fauzi. I'm a PhD candidate at University of Florida. I'll be presenting our work titled ProxRay, Protocol Model Learning and Guided Firmware Analysis. For problem and motivation, analysis of embedded firmware needs context, like hardware architecture, memory layout, protocols used. Now, due to a variety of needs, embedded firmware implement a variety of communication protocols. Now, these complex protocols do not have formal specification. So it requires significant manual effort to gain domain knowledge in these fields. For example, the USB 2.0 specification is about 650 pages. Bluetooth specification is about 3,000 pages. Once an expert has gained that knowledge, it takes a certain amount of effort to reverse engineer firmware with extensive understanding. Due to different architectures, different protocols, it is very difficult to port this knowledge from architecture to architecture, and it is difficult to reason about this device firmware. Now, why do we need to reason about these device firmware? So one example of malicious firmware is the bad USB firmware, which is implemented in a trusted mass storage device, a flash drive. When connected to the victim's computer, it can turn into a keyboard, a human interface device. So once it turns into an HID device, it can execute saved keystrokes within the victim's computer and take over the computer. So it is very important to use domain knowledge to analyze the internal workings of an embedded firmware. So once we have the domain knowledge of these protocols, the internals of the firmware, we can use that to find out device behavior, detect implementation bugs, and identify malicious components. One of our major motivations is that real-world firmware already contains implementations of these protocols, and these are developed by experts working in their corresponding fields for years. For example, now an example of these real-world firmware codes are these two from USB and Bluetooth code snippets. The USB one is provided by TI for the MSP430 microcontroller. So the red marked fields here represent protocol-dependent aspects within the code. So two major aspects here is that for the fields are first assigned some values, then the fields are checked for these values to take any specific action. The same thing happening in Bluetooth provided by BT Stack by Blue Kitchen. So it is very easy. The red mark fields are the protocol relevant fields, and the names correspond to their same names as specified in their corresponding specifications. So you can see it is easy to find out protocol usage from these code examples. Now, we use these examples to learn the model from known firmware. Problem in embedded firmware analysis is that source code is not that available always. So we extract protocol model from both source code and binary. And our analysis learns from real world implementation and practices. Our procedure is architecture agnostic. We do not dive into the details of hardware architecture, and our process is protocol agnostic. So we have applied our process on USB and Bluetooth, L2CAP, and HCI layers. Design overview. Our a ProXray works in 3 phases. The first phase is model learning phase. At this time, we learn from known firmware. Once we have learned from known firmware, we move into phase 2, which is field mapping. Now we try to map the learned model into the unknown firmware, test firmware. The test firmware can necessarily be a binary blob where we do not know which memory regions correspond to the protocol relevant aspects. Now, once we have mapped the protocol usage in the test firmware, we can move into model guided analysis, which is phase 3. So in the model learning phase, we provide a training set of known firmware. In addition to the training set, a known firmware set, we provide the field mappings, the red marked regions in the example code. So once we provide this to our protocol learning engine, we get a constraint-based model. What this constraint-based model necessarily records are the values that the protocol fields were compared against to take certain actions. Once we have generated this model, we can move into phase 2, the field mapping. Now we apply our knowledge to the unknown firmware. We apply the constraint model and the test firmware to our protocol field discovery engine. Our protocol field discovery engine provides us with the firmware, the protocol field usage in the test firmware. Once we have mapped the test firmware with the protocol usage, we move into the guided analysis phase. In the guided analysis phase, we provide our model guided symbolic execution engine, the test firmware, and the field mapping provided in we got from phase 2. And at this point, we can ask our engine some queries to gain the result. For example, for the bad USB firmware example I provided earlier, we asked what functionalities does this firmware contain. Our model and guided analysis was able to tell us that in addition to the MSC, the mass storage capability, it also has HID, human interface device capability. So all 3 of our phases use symbolic execution. For evaluation, we perform, compared to baseline symbolic execution, we gain high speedups in both protocols we used, and we use multiple heuristics that prioritize paths based on protocol field discovery. Based on that, we achieved 73.8 times speedup in USB and more than 100 times speedup in Bluetooth. The more complex the code is, we gain more speedup. Now for phase 2, the accuracy of our mapping, for our test firmware, we have achieved very high precision in accurately finding out the protocol usage. In most cases, we can 100% precisely find the protocol usage in the test firmware. For functionality discovery, our model guided analysis phase, we focused on type-specific constraints in our constraint-based model. Once we found the type-specific constraints, some interesting facts came out that the constraint we need to look at to find functionality of our test firmware seem to be a lot smaller than the whole constraint space. And using these type-specific constraints, we could find out functionalities of from multiple architecture test firmware. We used Intel 8051 and MSP 430. We were able to, our precision and recall in both places were 100%. We were able to correctly and completely find out the functionalities of our test firmware. To summarize our contribution, we are able to directly generate protocol model from firmware using several symbolic execution prioritization and pruning heuristics. We can automatically recognize protocol usage in test firmware. And once we have we have found the protocol usage, we can answer queries about the unknown firmware. We have applied our methodology to multiple protocols, the USB protocol and Bluetooth HCI and L2CAP layers. We have evaluated on multiple architecture, MSP 430 and Intel 8051. Thank you, and I can take questions now.
There's currently no question from the audience. I just have a very quick question. You mentioned that domain knowledge is very important in discovery the protocols, and this is applied to the USB and the firmware. Is there some additional application areas where your work can be applied?
Yes, we think so. So I think it can be applied to wireless and other protocols as well. as long as we have reliable source code to learn from, reliable sources to learn from. So once we learn this, we can apply it to unknown sources. Basically, our model extracts constraints from code. So the branches in the code are important. As long as we explore branches in the code properly, properly execute, say, most of the code, not gaining 100% coverage, I guess, we can extract a model from necessarily any domain.
I see. Thank you. Yeah, so this brings us to the next and the final speaker for the session, Rui Abreu. Are you ready for talking about the novel idea for visual sketching?
Sharing the screen.
Yes.
Can you guys see the screen?
Yes.
Okay. Can I start?
Yes, you can. Yeah,
Wonderful.
floor is yours.
Thank you. So this talk is about visual sketching, a technique to map images into code. My name is Rui Abreu, and this is going to work with Marcelo Damorim and Carlos Melo. Writing code is challenging. A variety of languages, libraries, and coding are available today to solve different problems. However, keeping up with all the choices available can be daunting. Programmers therefore make mistakes for different reasons. We propose visual sketching, a low-code approach to mitigate some of these problems. Visual sketching is a technique for program synthesis, an area that is mainly investigated by the programming languages and software engineering communities, but one that is intensely fertilized by machine learning. The visual sketching workflow consists of the following 4 steps. First, a developer defines a transformation from images into code. The transformation is a function that takes as input an image and looks for a matching image on an image database. If a match is found, the transformation extracts relevant information from the input image and generates code on output that is associated with that reference image. Second, a user writes an image describing their intent. Third, the tool looks for a match, and if a match is found, then it produces the code. And finally, the user fills the holes into the code. A hole denotes elements that were not inferred from the input image and should be completed by the end user. The following are 2 examples, both from data science domain where visual sketching can be handy. The first one is data wrangling, for example, going from CSVs and how to extract that information from a CSV. The other one is a design of a neural network where one can design visually the neural network and then we'll get the code like in the right-hand side. Visual sketching, as I said, needs to process images. As the image sketches are essentially a composition of text elements, they can be treated as documents. And document engineering is the research field that can study how to process these documents. At a higher level, visual sketching executes in 3 steps. We need to do structural analysis of the document, then document image segmentation, and finally text recognition. In the paper, we go into detail of all these steps. Here, I just want to say that at a higher level, one challenge to realize visual sketching lies in the tension between simplicity and expressiveness. Deciding the right balance between simplicity and expressive power of the visual sketches is one important challenge to realize this vision. The other challenge is the selection of advanced tech algorithms and algorithms that are efficient for this problem. There is a vast array of options of computer vision algorithms to use for solving these kind of problems, but we need to understand which ones are more appropriate to this, are more suited to this work. So to conclude, this paper presents this visual sketching, this bold idea for going from images into code. And this is actually a new research direction on code synthesis. We have discussed the main challenges in this work. In the paper, we're going to detail, as I said, into all these main challenges. Here, I don't have time to do that. And I just want to conclude by saying that this is work in progress, and we are happy to collaborate with anyone that wants to help us to realize this vision. Thank you.
Okay, so we don't have a question from the audience, but I do have a question to compare this approach with the model-driven type of approach. Is this broader in the scope where the code generation rely on already recognized model? And in your case, the model was very fuzzy or it's only like drafty, flexible models.
Right, and it can be handwritten, right? I mean, when we have a model, like if we follow, let's say, UML or some other sort of of representation, we are like we stick to that representation, right? So here, the way I draw things might be different than the way you draw things, but still, our vision is that this technique would still be able to generate code, but at a lower level, I mean, it's similar to that. It's like we have a model. In our case, it's an image, right? Model-driven software engineering is more like a UML or this sort of models, and then at the end we want to produce code, right? So that is similar in let's say in scope. It's just that the input is different, and in our case, because the input is drawn images, it can be much more, as you said, fuzzy, more difficult to understand what is part of the structure of the program and what is input, right? So this is the kind of things that we need to deal with.
Yeah, that's a great vision you have. I think it's still very ambitious, I would say. But if you achieve it, it will be really solving a lot of problems and everybody will become very productive. Oh, there's now one audience questions. If I got this right, is the end user expected to fill in the holes directly into the code?
Right. So if you go into the paper, I mean, I have one example here, if you guys can still see my slides, right? So on the left-hand side, I have the diagram for a neural network. It's a very simple one, right? And then on the right-hand side, what I have here is some question marks. And these question marks, as we see it, would be where the user would have to go there and fill what is missing, right? Because we cannot infer that from the diagram. So that this is like an abstraction that the diagram doesn't allow us to infer. In our case, what we also envision is that we have some options. Like, for example, here we say, okay, you need to provide here something. It might be ReLU or Sigmoid or, some options. But yeah, at the end of the day, we cannot infer the whole thing. And these holes that we have in the code is what the users will have to go there and input such that it solves their problem, right? It's not just the skeleton. So in a sense, we are just generating the skeleton and expecting the user to complete the whole thing such that they have a final program, right?
Yeah, that's a great answer to me and also to the audience. Thank you very much. Thank you for all attending and asking very interesting questions. Let's thank all the speakers as well. Now I think we close the session now.